Okay, it's been a few weeks, so time for another live session answering questions about astronomy for the online course. I'm welcome to take your questions starting now.
All right, our first question is from one of our live viewers who asks about the pictures we see of distant galaxies. They're so colorful, but when I look with my own eyes through the telescope, I see only blurred, misty objects without color. Are the pictures real, or are they made by Photoshop?
It's a good question because there are many pictures of galaxies on the web, and they come from reputable astronomy sources, from the Hubble Space Telescope, from NASA, from Kitt Peak Observatory, and so on. So the colors you see to your eye are obviously real colors. And yes, to the naked eye, well, Andromeda is the only galaxy you can see, and it's just a faint little patch of light if you live in a dark enough place. Or through binoculars or a small telescope, they are just pale, whitish yellow. And occasionally, if you look at an elliptical galaxy, there are not too many visible, but with a small telescope, you can see a few dozen. They can actually sort of look orangish, not fully red. So the color range of real galaxies to the naked eye or the assisted eye is pretty mild. The colors you see in the photos or digital images on the internet taken, say, by Hubble Space Telescope, they're real colors, but in a sense, they're sort of amplifying the capability of the eye. So they're not false or fully fake or photoshopped in that sort of artificial sense, because what the Hubble Space Telescope does is it takes, typically to make a color image, what seems like a color image is it takes 3 consecutive images with the telescope pointing in the same place through 3 different filters, typically a red, a green, and a blue filter. So if you held them up to a white light, that's the color of the light that would be passed through. Now, they then can take the digital images through each of those filters and weight the 3 to roughly mimic the sensitivity response of the eye. But in fact, the filters on the Hubble Space Telescope have greater sensitivity to longer and shorter wavelengths than the human eye. Human eye sensitivity falls off quite rapidly. And so the Hubble Space Telescope is sensitive with its CCDs to bluer or shorter wavelength and redder or longer wavelength light than the eye really is. So in that sense, it's amplifying what you could see with your eye. And that's partly what's responsible for the sort of enhanced sense of color with the Hubble image relative to the naked eye. The other thing that's happening is with those 3 images combined digitally, you can play with the color and also with the contrast, and that sort of makes the colors pop. That makes the dynamic range of the colors larger than you would get with the human eye. The human eye is a logarithmic device, which actually, in practical terms, means you have very limited dynamic range. So when you're looking at a pale, faint galaxy on a black sky, there's very little range of brightness from the black of the sky to the very feeble light from the galaxy. Well, with the Hubble Space Telescope, the sensitivity is great, and so the contrast between the galaxy light and the much darker sky background from space is greater. So you have greater contrast. So those are the 2 reasons why images, say, with Hubble Space Telescope that appear to be color are more dramatic than what you would see with the eye. But they are scientifically realistic in some important sense. And Hubble Space Telescope as a project has endeavored, and in fact is proud of the fact that they don't kind of release fake color images, lurid colors that are completely artificial and unreal. They always claim that their images are astronomically accurate.
All right, our next question is also from a live viewer, Ilsa, who asks, scroll down a little further. NASA sent the Parker Solar Probe to the sun. What kind of instruments work in that extreme heat?
Right. The Parker Solar Probe is an impressive instrument because it's going far closer to the sun, essentially entering the heliosphere or the edge of the chromosphere, in fact, than any other solar mission. So NASA's had solar missions before. SOHO was the most famous, which operated for more than a decade. It's been defunct for a decade now. The Parker Probe is a new generation telescope and instrument, so it's more advanced technology. It's getting a lot closer to the sun, dangerously close, you might say. And it's going to get much more sensitive measurements and resolve some of the issues that are still unresolved. It's named after Eugene Parker, who is a very famous astrophysicist in the physics department, actually, so physicist as well, at the University of Chicago. And he had essentially a 50-year career doing foundational work on magnetic fields, magnetohydrodynamics, gas dynamics, so really foundational physics, and then applied in astrophysics terms to the sun and the atmospheres of stars. So he's a very famous person, suitably worthy of having a satellite, a mission named after them. This mission is obviously built to withstand this much stronger solar radiation that it will experience, which is not just the electromagnetic radiation, just the light of the sun, but also the particle environment, because the solar wind is a stream of high energy particles. Protons are the most damaging because they're the most massive. And so this probe has to be able to withstand that too. So this was like a hardened probe that had quite a lot of mass, and was one of the reasons it was expensive and took a while to put together, because it does indeed have to survive a pretty hazardous environment. And the biggest issue there is that its very sensitive instruments have to be protected. They are measuring some forms of radiation and they're diagnosing magnetic fields, but they have to be protected from the forms of radiation that could damage the detectors, rather than just be radiation that can be sensed by detectors. So this is probably one of the most challenging missions NASA's ever built.
Right, our next question is again from a live viewer. Angela asks, how do we know black holes exist? How do you know that there is a black hole existing in a certain area of space?
The proof or evidence level for black holes has just gradually grown over the years. So black holes were hypothesized really at the beginning, almost 200 years ago, by John Michell, an amateur astronomer in England, a clergyman, who did astronomy in his spare time, and a very clever mathematician. And he used Newton's theory to extrapolate gravity to a dark, massive star where light couldn't escape. But you actually can't understand or truly predict black holes without general relativity. So black holes were first time predicted in the 1920s and 30s using Einstein's theory. Einstein himself didn't believe they would exist. He actually thought they were artifacts of the theory. So he didn't have his enough confidence in his own theory. So there was a period of about 30 years between the calculations in general relativity that suggested that if a massive star dies, its energy source is exhausted, then the core will collapse if it's massive enough, which is typically about 3.5 times the mass of the sun, to a state that's so dense that not even light can escape. And that's the definition of a black hole. And the boundary of the region, dividing the region between which information can flow and light can travel and nothing can flow and light and everything else is trapped, is called the event horizon. So that prediction was made in the 1930s, and it wasn't really until 1969 that the evidence accumulated to the point of, to most astronomers, proof beyond a reasonable doubt that Cygnus X1, a binary X-ray source, was a black hole. So given that black holes are by definition black, you can't see an isolated black hole in space. It would indeed be invisible. There actually is a clever way to detect them through gravitational lensing, but nobody's been able to do that yet. And so the 3 or 4 dozen black hole candidates that have raised to the level where no stellar astronomer doubts that they're black holes are all in binary systems, where the binary orbit is used to weigh or measure the mass of the invisible companion, and gas from the visible star is feeding onto the companion into an accretion disk, and there's a lot of high energy emission because material falling into a black hole accelerates, gets very hot, emits X-rays, and so these are essentially all X-ray sources. So after 1969 being the first, and now we've got a few decades since, really not that many, only about 40 or so stellar black holes, all in binary systems, all with X-ray emission. But really, to most astronomers, there's no other way to explain the dark companions in these systems. Now, I'll stop my answer there, except to point out that an entire whole field of astronomy now revolves around studying massive black holes. And the evidence for some of those, where the masses go from millions up to billions of times the mass of the sun, is also very strong. In fact, probably the best evidence for any black hole in the universe is not a stellar mass black hole in a binary system, but it's the black hole in the center of our galaxy with a mass about 4 million times the mass of the sun.
Our next All right, our next question comes from a live viewer who asks, what is the current leading theory on dark matter, and what does it mean if the WIMP theory fails? Will we have to redefine our understanding of gravity?
The short answer is possibly, because the WIMP theory, which is an acronym for weakly interacting massive particle, is still the default explanation for dark matter. So the identification of the dark matter particle is progressing, I would say, pretty slowly, and that's just because this is hard experimental work. This is not astrophysical or astronomical observations. This is physics work, measurements in mine shafts, typically, because you need to be shielded from cosmic rays and other particle events. Great detectors made of ultra pure semiconductor or large, tanks of fluid where the dark matter particle can interact with the fluid. So these are the kind of physics, large scale experiments that are being used to detect the dark matter particle. All other things than a subatomic particle, fundamental particle, have been essentially ruled out. And so that's where the hunt is. And so weakly interactive massive particles, WIMPs, are the best definition of a candidate, because a dark matter particle has to be massive, which is to say more massive than a proton, because remember, dark matter outweighs normal matter in the universe, most of which is protons, because most of the normal matter is hydrogen, by a factor of 6 or 7. So you do need, if dark matter particles are as abundant as normal particles, they have to be more massive. So that's what the expectation is. They're weakly interacting, the first two letters in that acronym, because they don't interact by the electromagnetic force. Otherwise, we'd have seen them. Dark matter particles that radiate or emit light or interact with radiation would have been detected decades ago. So we know they interact weakly or not at all with electromagnetic radiation. And so these experiments to find them are basically using collisions. They're using the fact that the dark matter particles, are traveling through space at some large velocity, and when they travel through a large mass of material that you have control of and can measure its properties, they will deposit energy in that material, or they will perhaps create flashes of light when they interact or collide with atoms in that material. So that's the method that's being used. And at the moment, there has been no success. So the WIMP, or weakly interactive massive particle hypothesis, is still on the table, but it's actually being ruled out steadily. The underlying theory for the WIMP is called supersymmetry. It's the idea that when 3 out of the 4 forces of nature were all unified in the early universe and had equal strength, the fourth one, an odd one out, is gravity. So this is the weak and strong nuclear forces and the electromagnetic force. Out of the merger of those forces, the unification of those forces, which is a premise of physics, basically, that there's not 4 fundamental forces in the universe, but one superforce, which at low temperatures in our universe manifests in different ways. The supersymmetry theory ends up predicting a massive stable particle that could have the properties we ascribe to dark matter, and that is the best candidate. And it hasn't been ruled out yet, but it's in a situation where the data is going to be able to rule it out in all reasonable senses within a couple of years. And what that means is that the simplest and most logical supersymmetry theories that predict a dark matter particle like that will have been ruled out. And so it'll be a double blow. It'll be a blow in physics to have not confirmed this article of almost faith amongst physicists for decades, that the supersymmetry underlies unification in nature, and also that astronomers will not have a viable candidate for dark matter particle. The next tier of candidates are much more exotic, things like axions and things that are part of the landscape of high energy and particle physics, but they're not as neatly predicted as a WIMP would be. So there'll be a crisis in astrophysics and astronomy as well as in physics if that happens.
All right, our next question is from Alexandra, who asks, is NASA or any other space agency developing an alternative to rocket engines?
It's a good question, just because NASA has been using essentially the same technology for 60 years. And so has the Russian Space Agency. I mean, it's kind of back to the future when you think that at the moment, the United States has not had the ability to get an astronaut into Earth orbit for 6+ years since the grounding of the shuttle, retirement of the shuttle. And we've been relying on Russians in the Soyuz capsule and the Proton rocket. Well, the Proton rocket is technology that derives from the late 50s, early 60s, and NASA's really only just using rockets even now that are descendants of the Saturn V rocket that got Apollo to the moon. And so that's a 50 or 60-year-old technology too. So it's a fair question that when is NASA going to jump to a new technology? So there is a small program. There are small experimental propulsion programs at a couple of the NASA centers. I think Johnson Space Center in Houston does it. NASA Ames does it. And a couple of the other centers do it, the less well-known ones. But it's not getting a lot of investment. I suspect that the total of these propulsion system research programs is maybe a couple of $100 million, maybe $200 million or so. And it sounds like a lot of money, but for this kind of high-end technology, that's not a lot of money. And as a fraction of NASA's $18 billion a year budget, that's not a lot of money either. So you're not going to get very far that way. Other space agencies have their own efforts. The Russian Space Agency is almost always broke, so they really can't afford much R&D. And the Japanese and other space agencies, the Brazilian and the Japanese and the Indians, other countries that have new space programs, they're pretty much just getting their feet. So they're using the existing rocket technology because it's cheaper and it's mature. The private sector, of course, is doing their best. And I would say Elon Musk and Jeff Bezos with SpaceX and Blue Origins have gone as far as they have, essentially by perfecting and honing that 60-year-old technology and making the rockets reusable. They haven't really changed the propulsion system. It's chemical fuel, volatile chemical fuel. So it's actually kind of a discouraging landscape, because to develop the next generation of propulsion systems, and there's a whole suite of them, that would be a separate question and answer to talk about that, is going to cost billions, and in the end, tens of billions of dollars of investment. And it's really hard to see how that's going to happen at the moment.
All right, our next question comes from a live viewer who asks, can you say something about the oldest known star in the universe that was recently discovered 2,000 light years away from us?
Okay, the oldest star in the universe. Yes, that was a story just from this past week. So it's a slightly indirect argument, because it's actually very hard to measure the age of individual stars. They really don't have their age written on them at all. For instance, if you wanted to measure the age of the sun, the closest star, and we know an awful lot about the sun, the age of the sun is actually a hard thing to measure. You actually have to make a model for the sun. What you can really measure for the sun is its mass and its luminosity and its temperature. And so you can make a model which tells you how old the sun is to be burning that luminosity at that mass since the time it formed, which is, we do know that. This star, the inference that it's extremely old is measured by its, what astronomers call metal abundance, or its abundance of heavy elements. Astronomers have a kind of simplistic, artificial and simplistic way of defining the periodic table. They say that the hydrogen and helium, which are primordial elements given to the universe in the Big Bang itself and a few minutes afterwards, are the sort of, again, the foundation stones of the universe chemically, and that everything else that comes from stars are called metals, which is just shorthand for all heavy elements beyond helium. So stars make all those heavy elements, and if you find a star where there are essentially none of those heavy elements, then it must have been made from the pristine primordial gas left over from the Big Bang. The longer the time goes after the Big Bang, the more generations of stars have born and died and spewed their heavy elements that they made and mixed into their atmospheres out into space. So the fraction of heavier elements than helium rises slowly and steadily in a galaxy like the Milky Way. There's also a variation in that abundance with distance from the center of the galaxy. So it's not all the same chemical abundance everywhere in the galaxy, but you can make a model for that. So this star essentially, through spectroscopy, been shown to have less, I think, than a tenth of the abundance of heavy elements of the sun itself. And in models of how stars form and evolve, that suggests that it formed extremely early in the history of the galaxy and therefore also of the universe within the first billion year after the Big Bang. And that's important because, it's actually hard to say when the Milky Way formed, since the Milky Way formed by mergers and acquisitions, smaller dwarf galaxies gradually combining to form a bigger galaxy. So the Milky Way has grown in size and mass steadily. So finding one individual star that dates back to the birth of the whole thing is pretty important. And so this is a very important and significant observation, even though it's just one star. Obviously, people are trying hard to look for more stars like this. They're called metal poor stars because astronomers call these elements that are heavier than helium metals. And they typically, the metal poor stars tend to be in the periphery of the galaxy, in where the globular clusters are in the halo. So you look up or down out of the disk to find such galaxies. And there are others that have been found. This is just a particularly extreme one. So this is very important research because it's sort of the archaeology and history of the Milky Way galaxy we inhabit.
All right, the next question from a live viewer is from Digital Cosmos, who asks, can you say something about, can we calculate distance and this is actually from Kushal, my apologies. Can we calculate distance in the universe using baryonic acoustic oscillations? And if so, how?
Yes, it's considered a sort of cosmic measuring stick or meter stick, obviously measuring big distances, not meters. So first we have to understand what a acoustic oscillation actually is, a baryon acoustic oscillation, abbreviated BAO. And so it's a subfield of cosmology, observational cosmology. So basically, in the time of the universe up until normal stable matter formed, or neutral atoms formed, which is about 400,000 years after the Big Bang, the material of the universe, the baryons, which is the normal particles, the protons and electrons, typically neutrons, were moving around at a very high energy and high temperature. And the oscillations that are referred to in baryon acoustic oscillations are sort of oscillations that are imprinted by the amount of distance they can travel in that early universe. So basically you can have one wave of oscillations where the wavelength is the size of the observable universe at that time, or you could have a harmonic of that, 2 waves, 3 waves, and so on. And the baryon acoustic oscillation signature is one wave, one full wave, or one half wave actually, peak to valley, of radiation oscillating with baryons in the early universe before stable atoms formed. So it's looking back to the state of the universe 400,000 years after the Big Bang, very early on. If you measure the strength of that signal, then you actually know in physical terms, in distance in kilometers or some physical unit, what the size of the universe was at that time. And if you then look to the nearby universe, you can try and see the effect of that signature as it's been diluted by the expansion of the universe over time. And in fact, surveys were done, and I think the first measurement was by Daniel Eisenstein, one of my colleagues who since left and went to Harvard, was done here, was using the Sloan Digital Sky Survey. And he used the galaxy distributions of the several million galaxies in the Sloan survey to measure these acoustic oscillations in the more recent universe after much cosmic time has passed by. And because we think we know how much the universe has expanded, we know how much that length, that physical absolute length, should have changed over cosmic time. So it sort of becomes a test of the expansion and the cosmological model. So it's valuable in that sense because it's one of the few pieces of physics going on in the early universe that leads to a scale length in absolute units or kilometers.
All right, our next question comes from Zahir, who's on with us live, who asks, if we consider the sun and Earth as 2 points in a plane, then there must be a point exactly located on top of the Earth where the sun never sets or rises. Is that true?
It would be true if, the Earth were not tilted in its spin axis as it goes around the sun. So if you imagined the Earth and the Sun as points in a plane, as you say, and that the Earth, and then also add the fact that the Earth is spinning once per day while it goes around the Sun every 365 and a quarter days, then yes, if you were on top of that little spinning globe or directly on the bottom of that spinning globe, the Sun, those would be the places where the Sun would never rise and set. But since the Earth is tilted by 23.5 degrees, its spin axis is tilted with respect to that plane defined by the Earth and Sun. There is no such place where you never see the sun rise or set. Rather, there are periods of time of the year when that can be true. So obviously, in the northern hemisphere winter, that corresponds to a time when the North Pole of the Earth is tilted away from the sun on that side of its orbit. And so there, of course, you do have places going down to a latitude of 90 minus 23.5, which is 67.5 degrees, and that defines the Arctic Circle. Anywhere above that latitude will be places in that period of the year where the sun never rises or sets, and the converse is true in the southern hemisphere.
Right. Our next question from Kushal again asks about Reisner-Nordstrom metrics. And first of all, he would like to know what a metric is, and then also how can Reisner-Nordstrom black holes acquire an electric charge?
So I like Kushal's questions. They're very high level. They're probably maybe a little too high level for most of our viewers, actually, because I can't give a whole lecture on a subject like that, unfortunately, outside of graduate class. A metric, that's easier to answer, although not trivial, because metrics are constructs that emerge out of general relativity. So the word metric, as opposed to the metric system of units, which is how most people understand that word, in astrophysics, metric refers to a description of space-time. So in general relativity, where you're considering all possible space-times and curvatures of space and relationships between space and time in gravity theory, then the metric is a sort of fundamental, it's an essential piece of any calculation in general relativity, because it essentially tells you how space and time map in the cosmology or the situation you're considering. And so the normal universe that we inhabit, where gravity is generally weak on very large scales, is described by what's called the Robertson-Walker metric, or the Friedmann-Robertson-Walker metric, FRW or RW metric for the people who first came up with it in the 1930s. And that's a sort of, as I mentioned, gravity being weak, it's a sort of gentle space curvature situation where you describe how particles and radiation travel through the curved space. And so to work in general relativity, to do calculations of the universe, its future evolution, and so on, you use the metric, the Friedmann-Robertson-Walker metric, to do all your calculations of distances, of redshifts, of anything, of angles, of anything you might measure. Now, the metric that Kushal has asked about in the question is one of a handful of black hole metrics. So black holes also can only be understood in general relativity. So once again, there are space-time situations where you need a metric to describe the relationship between space and time, the way particles travel through that space-time, the way radiation travels through that space-time. And so black holes have metrics. Now, the first metric was defined by Kerr, Robert Kerr, sort of famous mathematician and physicist, Canadian actually, 50 years ago or more. And so the Kerr metric is the metric that describes a non-rotating black hole. When you have a rotating black hole or a rotating black hole with charge, you actually have to use different metrics, hence the question. And so there's a handful of other metrics out there which have names attached to them from the physicists that worked them out to describe not just esoteric, but actually slightly more realistic situations of black holes that are rotating as opposed to stationary, black holes that have electric charge and are rotating or are not rotating, and so on. It's extremely hard to calculate gravity of a black hole in any metric, and there's only a handful of metrics where those calculations have ever been done in the history of relativity for black holes. The calculations are just that hard.
All right, my apologies. I was just making a quick sound adjustment. Our next question comes from Behan, who is online with us live, who asks, is it possible for a star whose inner layer is radiative and outer layer is convective to switch these layers such that the inner layer is completely convective and the outer radiative?
That is not seen in stars that we've studied. So to rewind to what underlies the question, in a normal star like the sun, for example, radiative transport occurs in two different modes. It occurs by radiation, and in this core of the sun, that radiation is, of course, interacting with a plasma, because the sun is a fairly dense plasma, denser in the middle than further out. The central quarter by radius of the sun is the part where the fusion reactions occur. And then beyond that, the radiation is diffusing out in a sort of random walk, a sort of drunken man's stagger, if you like. The radiation hitting a particle, typically an electron, and then going off in a different direction, losing a little energy, and then hitting another electron, and so on. So the radiation diffuses out. So that's one method by which energy flows out of the core of a star. Now, in the outer parts of the star, until you get to the photosphere, what we would see as the surface, the mechanism of convection can occur, which is essentially circulating parcels of plasma, very analogous to the convection you would see when you boil a pan of water on a stove, where when you get to a certain temperature, the heat can't actually flow upward through the water to the top of the pan efficiently enough, and so the large pockets of water start circulating up and down, transporting the heat sort of in bulk more efficiently. And so that's why water boils, and that's why it boils in that particular way, as opposed to just evaporating off the top surface of the pan. You know, people wonder, why does water boil that way, in that violent way? Well, the star is doing the same thing. So because of mechanisms of physics and radiation flow and energy transport, there's no feasible way a star can reverse the positions of its two modes of energy transport. And essentially all stars we've studied operate about the same way.
Right, our next question is from Alexandra, who is online with us now, and asks, do you think that Soyuz spacecrafts will still be used after the accident?
Well, the accident you're referring to is, of course, there was a potentially fatal accident. An American astronaut was involved too. I forget if there are other Europeans or international astronauts on the capsule. So that was what should have been a routine flight to the International Space Station, where again, Soyuz is the only capsule that can do it. And it was a very difficult and potentially disastrous landing after a problem with the rocket. So the Russians have shut down their launch program because of it. They have to, of course, have a full investigation. It's the only way anybody can get into Earth orbit until Elon Musk or Jeff Bezos figure it out in a year or so, and they probably will. So they've shut down their program, and they're pretty tight-lipped about how long it'll be before they finish their investigation and fix whatever the problem was and start launching again. I'm going to guess it's another year.
All right. Our next question, again, comes from a live viewer who would like to know if you have any thoughts on the comet Oumuamua and the recent paper that was published.
Right. So it's an asteroid. I mean, it's defined as an asteroid. It's actually an interloper object, but it's a rocky object. It's not particularly a comet, because a comet suggests a captive member of the solar system with a highly elliptical orbit. And I think the key to this object, which everyone will know when I say that it's the needle-shaped rocky object whose picture appeared in the press frequently about a year or so ago when it was discovered coming into the solar system, it's an extremely elongated object. There's no asteroid or solar system object even close to as elongated. It's the ratio of its length to width, I can't remember, but it's more than 10 to 1. So it's like a needle, almost a rocky needle in space. So that caught people's attention. And the more recent interest in the object, apart from the fact that it's still pretty extreme in terms of its shape, is that the study of its orbital trajectory really suggests that it came from very far away, that its that it is not originating in the solar system. It's not just on a long looping orbit like a comet where eventually it comes into view, but could spend hundreds of thousands of years in the deep freeze of the Oort cloud. It really seems by its orbital elements to have come from beyond the solar system, from another star system, because obviously, rocks of that size don't just exist in interstellar space. They have to be produced near a star and built up by accretion. So it's come from another star system, and that's led to all sorts of speculation. It's not implausible that that could happen. There are means by which objects of that size can be ejected, gravitational slingshot mechanisms, the ones we use to accelerate spacecraft under some circumstances. They can eject objects from a star system. So it's not impossible for star systems to eject objects. This is a pretty unusual object, though. And so the kind of edgy speculation is that perhaps it's the product or the emissary, if you like, or a signal of an intelligent civilization. And one paper that's published in the archive where astronomers publish their research before it goes to peer-reviewed journals, it's almost has the feel of a spoof article by two authors, one of whom I think was until recently was the head of department at Harvard, speculates that it's a solar sail that actually is not only an emissary by an alien civilization, but that they beamed radiation onto it to get it to the very high speed required to leave its original solar system and arrive at ours at such a high speed. That's pretty extreme speculation, just based on its motion. So its strange shape and strange motion is leading to all sorts of speculations. And of course, it's fun to speculate and it's fun to talk about aliens and civilizations and all that. But I mean, the truth is, it's probably got some interesting, but in the end, more mundane astrophysical explanation. But it's still a very interesting object.
All right. Our next question from one of our viewers is about the Earth and its motions in the solar system. Why does the Earth continue to orbit and rotate without losing speed?
Well, it's a good question, and the correct answer is that it does, and it does lose speed. And so there are there are real but very, very slowly operating processes by which an object that's spinning will lose angular momentum. And typically, it'll lose angular momentum by transfer. Angular momentum is conserved in astronomy and in physics and astronomical systems. And so if the Earth loses angular momentum, it has to transfer it to another object. And in the case of the Earth, that other object is the Moon, the closest object. And the Moon and the Earth are in a tight, tidally locked situation. They're the Moon showing its same face to us all the time. And so the result of that tidal locking and that strong gravity interaction between the Earth and the Moon is that the Earth is indeed very, very slowly slowing down in its spin rate, and the angular momentum, the energy and angular momentum transfer is moving the Moon very slightly slower away, more away from the Earth. I think the amount is not trivial. It's like 4 centimeters a year. That's tiny compared to 250,000 miles, but it's a measurable effect because of the reflectors the Apollo landers left on the Moon, letting us bounce signals and do actual distance measurements extremely accurately. So yes, objects like the Earth in their orbit, in the Moon's orbit of them, and in their orbit of the Sun are slowly losing energy, transferring it to the medium they move through, which is not a perfect vacuum, or transferring energy or angular momentum to companion objects that they're in orbit of. So it could be the Earth and the Sun, or the Moon and the Earth, or it could be the entire solar system and more nearby objects, the larger stellar environment. That's an even slower process. But these orbits and these spins are not long-term stable. They are slowly changing, very slowly.
Our next question from a live viewer is from Jane, who asks, what is the shape of a black hole?
Well, the black holes in the real universe should not be spherical because they should all be rotating. So they will be what are called oblate spheroids, which means, as with any mechanical object that you can think of, when it's spinning, it bulges slightly at the equator. So a black hole, or rather the event horizon of a black hole, that we can measure or interact with or diagnose, will have that shape, sort of like a sphere, but it's bulging slightly at the equator. So that's likely to be the true shape of a black hole.
All right, our next question is from a live viewer who asks, how did the supermassive black holes in the center of our galaxy and most massive galaxies form?
It's thought that they formed from seed black holes. The galaxies all were originally smaller. The Milky Way, for example, we believe to have been assembled from possibly hundreds of smaller galaxies merging over time, much of that happening earlier in the universe, and the rate of that addition slowing down. But we see evidence of it now. So there are very careful studies of star motions in the Milky Way, show streams, show evidence of galaxies that fell into the Milky Way, adding a little to its mass in some part in the distant past. And of course, Andromeda is heading towards us, so there will be a major merger of two big galaxies in our future. So that's how galaxies have been assembled over time from smaller pieces, an original situation, of course, where there were no stars and galaxies. And the black holes have done similar, because when two galaxies merge or combine, each with a black hole, the black holes combine. There is actually a small chance that, depending on the way the two galaxies approach each other, that the interaction of their nuclei could eject one of the black holes, so to just sling it right out of the combined system. And then you'd have a free-floating massive black hole in intergalactic space. That's pretty interesting. So that's the mechanism. And the question of which came first, the little black hole, which by little I probably mean 100 to 1,000 times the mass of the sun, or the little galaxy, is actually not known. At the moment, based on theory and fairly difficult simulations, the best betting is that there was a generation of massive early stars called population 3 stars or primordial stars that gave rise to a little population of not trivial black holes like 100 times the mass of the sun, and that those were the seeds around which nucleated the first dwarf galaxies, and then all the combination happened after that. But that's not definitive at this point.
All right, our next question is, does the sun give off wavelengths of electromagnetic radiation other than the visible light we see on Earth? And do other stars give off other electromagnetic radiation other than visible light?
Yes, they do. So the bulk of the sun's radiation is, of course, defined by its visible spectrum. And so because the sun looks like a yellow-white star, if you just made the light into a spectrum, you'd see it peak at yellow sort of wavelengths and fall off to the blue and to the red. Now, the nature of the thermal spectrum is that the fall off to the blue is more rapid. So it doesn't emit a lot of very short wavelengths, but it emits substantially longer wavelengths, just a diminishing amount as you go redder and redder. So beyond the red end of the visible spectrum, the sun is still emitting radiation. If you extrapolate that, though, to radio wavelengths, the sun is really not emitting many radio waves at all. The sun is detectable as a radio star, but that's only because it's so close. The radio emission is truly feeble. Now, at the high energy end, it's a little more interesting, because that is the radiation that emerges from the nuclear furnace, the nuclear core of the sun, after it percolates its way out to the visible edge, the photosphere. Visible light tailing off in the short and long wavelength direction. But also the sun is an X-ray object, so seen from afar and known for decades, the sun has extreme X-ray emission and exotic and active and changeable X-ray emission. And that X-ray emission comes from its corona. It comes from a diffuse high-energy plasma, obviously very high temperature. To make X-rays, it has to have temperatures of a few million Kelvin. So the corona is a very hot, diffuse outer region of the sun that was seen by X-ray telescopes decades ago and now is studied in a lot of detail. And so that's the other form of electromagnetic radiation that the sun has. But it's not the sun itself. It's beyond what we see as the edge of the sun. The understanding, as we have so far, it's not completely understood, is that energy, normal solar energy, the kind of visible radiation we see, travels out And there are acceleration processes whereby in a diffuse plasma, it can accelerate particles sufficient to produce X-ray emission. And that's how you can get the strange situation that as you go out from the visible surface of the sun, the temperature suddenly gets really high. It's very high, but it's in a very, very diffuse medium, far less dense than the sun itself.
All right, our next question is from Tatiana, who's on with us live, who asks, is there some kind of special order of naming cosmic objects? What do numbers and letters stand for? For example, there's a galaxy named NGC 5033.
Right. So the naming of astronomical objects, in particular galaxies, extragalactic ones, is interesting because there's a long history there, and the example used of NGC objects is one of the oldest parts of the history. Even older than that are the M objects, the Messier object, because Messier was a comet hunter, a Frenchman, obviously, working at the end of the 18th century, and he did the Messier catalog around that time. He didn't know what these objects were. We didn't know many of them were galaxies. Few were pulsars and supernova remnants until fairly recently. He made it was a list of fuzzy objects that were, he was interested in comets, basically, in fuzzy objects that moved across the sky. And so he made the Messier catalog for comet hunters to avoid, because these were objects not moving, because we now know they're much further away. It was a rather ironic situation, because this was his reject catalog that turns out to be very interesting. So that was the very first galaxy catalog, or catalog that contained about half galaxies. Somewhat later into the 19th century, in the mid-19th century, the NGC catalog, New Galactic Catalog, of thousands of objects now. Messier is just under 150. The NGC catalog was built by the Herschel's family, three astronomers in the family. And that they were looking now for fuzzy objects or nebulae. So these are a catalog of nebulae. They still didn't know what a galaxy was back then. And those are the two biggest catalogs, historical catalogs, that include galaxies. But now, of course, the naming is all over the place, because every major telescope that finds new galaxies as yet unseen can name them. And so especially like the Sloan Digital Sky Survey, it will have a prefix for all the galaxies it has found of SDSS, and what comes after is just a long version of the position name. So they don't actually have names. They just have a designator, which is the project Sloan Digital Sky Survey, and then a long number, which is a coded way of saying where it is on the sky. So galaxy names are not actually very exotic anymore. They're just tied to the project and the telescope that found them.
All right. Unfortunately, we have to leave a little bit early today, so that's our last question. Thank you, everyone, for joining us, and I'll let Chris say goodbye to all of our viewers.
Yes. Thanks very much for your questions. They're great as usual, and we'll be back in a couple of weeks. We'll try and keep the pace up before the holidays and get a few more in. Okay. Thanks, everyone, and goodbye.